Hey guys, I'm David. I did pretty good in Battle of the Brains, but I know some of y'all have questions because this is pretty hard. It's a pretty hard contest for beginners, and I don't want to I don't know. I want y'all to learn. So I'm gonna go through all the problems and all the solutions, and try to understand what's going on and hopefully learn. So this contest was just me and Sam, so you can kind of see who did who. I did in C++, and then Java did or anything Java related is Sam. So here it is. Just I did Comportal, Cadgar, Split the Vote, Wordle, and Whoosh. But Sam did all the other stuff. So what I'm gonna do is anything I've solved, I'm just gonna look at my old code, and then anything Sam solved, I'm just gonna code it out, see if I can get it right. Yeah. So in Indian military, each of the N soldiers is assigned to the corresponding proficiency score, where the I soldier has a score of PI. The captain arranges all soldiers in a straight line, 1 through N, such that their proficiency score is non-descending. A soldier is considered odd if the parity of one's position differs from the parity of one's proficiency score. Okay. You are to determine what the number of odd soldiers. The parity of an even number is 0, and the non-number is 1. Okay, parity is just even odds. So non-descending order is basically increasing, but two adjacent elements can have the same value. So I think I said this earlier, but this is called strictly increasing, meaning that if this was an array, like called A, AI is always going to be less than AI plus 1. And then here, this is called non-decreasing, so the opposite of decreasing, meaning AI is less than equal to AI plus 1. And then there's also others like strictly decreasing, which is going to be like 5, 4, 3, 2, 1. And then this is when I is always going to be, there we go. And this is going to be non-increasing. Non-increasing. That's kind of the differences. You can get them mixed up, but just remember, like, this is kind of the opposite. So, just count the number of odd ones. This shouldn't be bad at all, actually. Actually, I'll just, doesn't matter. 1, 2, 3, 4, 5, 6. I don't think we're just counting the number of odds, so. Since it's 10 to the 6th, and integer goes to 10 to the 9th, I'm not going to worry about any our integer amounts, so this is what I'm going to do. So n is going to keep track of all my, this is just input. N is going to keep track of all of my, I guess, what do you call it, soldiers, right? I think that's what it's called. And so PI, constraints. I think this is element of, it's annoying. Yeah, wait. Notation cheat sheet. I bet there's one out there. Oh my god. Let's see. Don't mind me. I have a virus on my computer, so that's why I'm using Bing. Doesn't have it on here. Whatever, here you go. Okay. So, yeah, this is just like, I think the value of PI is less than that. P is the soldiers, I'm guessing. Yeah, score. It's odd if one position differs from its parity. Let's see the explanation. The captain arranges the soldiers in non-decreasing order by proficiency, so the order of the proficiency scores are 2, 3, 5, 8, 11 up. Okay, so it sorts it first. So the first two soldiers have 2 and 3. Thus the parities of their position differ. Parity of 1, parity of 2. Okay, so they start by 1. I think I get a solution. That's it. So this is just an array list. Array list of stuff. This is just array list dot add. SEN. And then I'm just gonna sort. Yeah. So this is just arrays. That's actually I prefer y'all to use collections.sort. But your preference. I wouldn't use arrays.sort because there's a chance for it to be O(n squared, which is a little slow. I'll make this one. So I like it big. Like that. Okay. What I like? Wow, actually that's actually much nicer. Okay, so sort. This stands for count. I suck at typing. I'll just leave that. Usually in contests, I won't worry about this, but if you're coding in front of me, I will criticize you for it. So this is just array list dot get I. So for C++, vectors or array lists, you can access elements just like arrays, which is really nice. But yeah. So how this works is basically I just sort it with collection.sort, and then I go through the array, and if the parities don't equal to each other, should be down actually. If they don't equal to each other, yeah, if they don't equal to each other, then we add one to our total answer. And if we do equal each other, we don't add them. I'm just gonna run code. Looks like we got it. Submit. Tick tock, tick tock. Nice. That was not too bad. You just sort it, then you add it, check its parities. Not too bad at all. Whoosh. Okay, I did do whoosh, so I'm just gonna copy what I did. So what I did was, it may even be harder to read because of all the template stuff. This is just input. So I input, it says that, basically, okay. So how it goes is like this. They give you whoosh. They always give you whoosh. It's like, there's no point. They give you whoosh and then a number. So if it's 0, you print out mini whoosh. And if it's 1, you print out you print out 1 plus this number. So like consider this as x. You print 1 plus x o's in whoosh. For example, for 1, 1 plus 1 is 2. So you have to do 2 o's. For here, 4 plus 1 is 5, so that's 5 o's. And then you just print out whoosh all in capital letters. That's it. So right here, I just do input. And this is just output. Print line. So if n is 0, or if x is 0. So first I get the string, and then second I get the end. If n is 0, I just print out mini-whoosh. Otherwise, I'm going to print, not print line, I'm going to print here, and then I'm going to print n plus 1 O's. Okay, so this is n. Sorry, I said x earlier, but yeah. Then I'm just going to print sh, exclamation point, at the end. So all in one line, and then I'm going to print line. I'm going to print a new line here, just in case. That's really it. Yeah, that's whoosh. You just print out the number of zeros plus 1, or this number plus 1 zeros, or O's. This is not a hard problem. Okay, so comport is a little different. So I did get some wrong test cases, which is kind of sad, but it is okay. I bet if I didn't get the wrong test cases, I made such a dumb mistake too. If I didn't get the wrong test cases, I would have definitely got the problem, or definitely got first. But it's okay. I'm a little salty. So, here's the deal. The product of the first k composite numbers is defined by comportal, or simply ck. Given I, blah, blah, blah. Let's ck, blah, okay. It's better to show paint. So, let me check if everything's working. I think it's working. So, wait, sorry. Okay. Let me do my, no. So how a comportal works. So you have prime numbers and composite numbers, right? So let me get my, pen out. Get my pen. Okay. So I solved this problem, but Sam was actually pretty close. So there are two types of numbers, right? There's prime and composite. So prime numbers only have 2 divisors, and composite have 2 plus, or 3 plus. Divisors are 1 and itself. And that's pretty important, but yeah. So what a comportal is, it's the product of all composite numbers together, up to k. Okay. So k composite numbers, ck. And, like, for example, if this is the product symbol, so you may have heard of sigma, that is the addition symbol, and then this kind of pi like thing is, I forgot what it's called, it's like phi or something, but that is product. So, for example, I know it's like all mathematical and stuff, but you'll get used to it. So, imagine this. If k was 2, what are the first 2 composite numbers? Well, the first 2 composite numbers, let's see. Let's not count 2. 6, 7, 8. So, we're not going to count 1. 1's kind of iffy. I'm pretty sure it's not prime, but they don't count it in this problem. So, 2 is a prime number, so we're going to X that out. 3 is a prime number, but 4 is not a prime number, it's a composite. So that'll be our first composite. 5 is a prime number, and then 6 is a composite number. It's 2 and 3. So you'll notice then the multiplication of the first, or the product of the first 2 composite numbers is 24. That's a comportal. Okay. If I asked for the first 3 composite numbers, well, 8 is the next composite number, so the product of all that would be 192. That's the idea. Now the question here is, yeah, so they give you 2 number, or 1 number, and that is, they call it I. And that represents they want, so what pi stands for is like the ith prime number. For example, so the first few prime numbers, let's see, let's just write out some. So 1 is I still don't even know if 1 is a prime number. I'm pretty sure it's a composite. I don't know. Anyways, 2 is prime, 3 is prime. So if I wanted to find like the 5th prime number, 5 is 5. 4 is not, it's a composite. 5 is prime, composite. 7 is prime. 8 is composite, 9 is composite, 10 is composite, 11 is prime. Crap, my wires. So this is what's going on, right? So the ith prime number or the 5th prime number would be 11. In the sample, the first prime number would be 2. Okay. The second prime number would be 3. I think it says in the explanation. Yeah. First prime is 2, and then I guess they automatically assume 3. So then here's the next thing. So ck is the function. They call it ck. They sometimes put subscripts. But ck is the corporeal up to k. Got it? The corporeal up to k. Okay, like we said earlier, that is the product of all composite numbers, of all the first k composite numbers. The question is, what is the smallest k that we can make it so that it's divisible by the ith prime? That's a lot of stuff there. All right. So let's go back to the example. So the 5th prime number is 11, right? Right. The 5th prime number is 11. What is the smallest corporeal that is divisible by 11? Okay, let's try that. So corporeal. Okay, let's just draw out all the numbers. 14, 15. Actually, let's make this faster. Let's do 4. No, I like 11 actually. Screw it. We'll do 11. We're going to 22. Why not? There's a reason, but whatever. So 1, I'm just not gonna count. 2, 2, 3, 4 is composite. 5 is prime. Composite, 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 composite. Okay. What is the sum of all of these numbers? Oh my god. Okay. Actually, yeah. Okay, so please load. My OBS is not crashing. Please don't crash. Okay. Calculate, or please don't break. Please don't break on me. Please don't break. Oh. No, I just want to catch it here. Just give me a calculator. And also, like, why else is it Microsoft being? I still don't know. Oh my god. Get me out of here. There we go. Okay. 4 times 6 times 8 times 9 times 10 times 12 times 14 times 15. Let's make this smaller. Times 16 times 18 times 20 times 22. that's that. Five five 18098432000. That is a lot of stuff. Okay. So, okay. Here's the deal. I'm going to divide by 22 real quick. So we know, like, we're looking for a comportal that is divisible by 11. Okay, in this example. If I was 11, or it was 5, the fifth prime is 11, and we need to find a comportal that is divisible by 11. That is the problem. And we know this number multiplied by all these is divisible by 11 because 22 is divisible by 11. Okay. And I think it's like the fundamental theorem of arithmetic or something, but if one of its factors is divisible by 11, the whole product is divisible by 11. Okay. That's a pretty key math thing. Okay. So since 22 is divisible by 11, well, that means this whole thing is divisible by 11. So let's just check real quick. See, look, there's no decimal. Now, if we take out 22, you'll notice that all these numbers are not divisible by 11. So let's divide by 22. And this number won't be divisible by 11 to these dots. Okay. So, like, the main, like, trick with this problem is that, like, obviously this comportal is huge, right? We've already reached, what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 places, 10 to 13. In fact, this is just like the, what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The 12th composite number, like, the composite numbers go up to like 50,000, you know. So, in order to combat this, there's actually a pattern. And the big pattern is that, like, because of how prime numbers are structured, right, the smallest prime number, or the smallest composite number that has a factor of a certain prime is that number by 2, multiplied by 2. So in this case it would be 22, right? So if you think of any prime, the smallest composite number that is divisible by that prime is that multiplied by 2. And that is because, like, composite numbers have multiple factors, right? And so if you did some, like, prime factorization of, like, 22, it would just be 2 and 11, right? The smallest prime number is 2. Multiply that by the prime number that you have, you'll get the smallest composite number. That's kind of how that works. So, using that knowledge, right, one thing you'll notice is that we could only have a number that's divisible by 11 once we reach that 2 times pi number, 22. Otherwise, we're going to have a decimal like here. Like here. Okay. So, we have a couple steps here. First step, find the prime. Find the prime. So the example is like 5th to, so I was 5, and you have to get the prime number 11. The second step is to find pi times 2, the composite number. Okay, which you just multiply that by 2, so that'll be like 22. And then you find the index. So what I mean by index is that the final answer is k. So, right, when we're going through all the composite numbers, right, it's the product of the first k composite numbers. right? And so the smallest composite number is pi times 2. We got to find when the, like, what k is at 22. For example, if we had the, crap. I'll just write it out. Right, so all the composite numbers are here. Here k would equal to 1. Here k would equal to 2. Here k would equal to 3. Right? Since they're all multiplied to each other, they're also all factors. Right? So we can look at them individually. So the first time you reach, like, you gotta find its index. Okay? Here's index is 1, here, this index is 2, and this index is 3, and this index is 4. And so 22's index would be like, I forgot already. I think it was like 15. I don't know. You gotta find whatever index it is in terms of composite. So if I had like an array list of all the composites, I'm trying to think of all the composites, right? I'll get to. I may not get all the composites. Like, I may skip some. 21 is composite. Right. We got in an array list. We got to find what index it is at. So in this case, it would be 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It would be 13. K would equal to 13. Okay. And then you would print out 13. That's the goal. Okay. Why is OBS like that? Okay. So recap. Find prime. So 5 would become 11. 2 would be find composite. And that would be 11 times 2. And then find index. Those are the 3 steps. So how do we do this? Okay. Just going to go to my code. So first things first, this solve array is kind of... So we're going to use a strategy called pre-processing. Okay. Actually, I'll explain that later. So what we use is called the sieve of Eratosthenes. Something like that. I can't spell. Anyways, the idea is we do a basically O of n root n algorithm that basically generates all primes. I may do a video on it later. But basically, we know that a number is composite. Like, this is kind of what it looks like, a short look. I'm going to X out 0 and 1. So 2, right, first it labels everything prime. Okay. So it goes in a for loop starting from 2 and then to the square root of n. Yeah, but that will be explained later. So it goes here, and then 2, what it does is, okay, we know 2 is prime, and if we add 2 to it again, that's essentially 2 times 2. And if we add 2, that equals 4, so that number is not prime. That's kind of how it works. Okay. If we add 2 again, that is essentially equal to 2 times 3, which means that 6 is not prime. That's the strategy. And it keeps on multiplying till it reaches n, or whatever your array size is, and then it stops. And then it does that for every single prime number. That's kind of a sneak peek. But the sieve, so I'll give you a Google or a video on sieve. But the sieve helps us get our primes. Okay, so right here I'm adding to an array list. Like this is add essentially. And then I'm adding to my array list. And then I'm also going to count I'm going to have an array list of size, whatever this is. The reason why it's that times 2, because the prime number size, the highest prime number is around 500,000. And remember, it's like pi times 2. That is the smallest composite number that includes that prime. So I have to multiply by 2 as well. That's the idea. Okay. And so I'm going to make a whole array of size that. And if the number is prime, the value is going to be 0. But if the number is not prime, it's going to give me my index. Okay? And so notice here, if it's not prime, I'm going to set this is my index. I'm going to set my index to x. And then I'm going to add x plus. That's essentially the same thing. Okay. That's going on there. So that helps me get my index. And then I just multiply by 2 right here. So this is my smallest composite number, and then I multiply by 2. This is sort of the same as non UTD there. It's just for something else. But, yeah. That's it. I do this all in pre-processing. So, like, notice how there's, like, test cases? I do it before the test cases because there'll always be the same primes and the same composite numbers. They don't change. So, yeah. It's just better to access it with an array. So technically, the solving part of the algorithm is actually O1. This part is just the same constant time 2. This is actually technically constant because none of this involves n. This n is actually not even n right here, but whatever. Yeah. That's corporeal. This may be a little too advanced for y'all, but just like the gist of it. I'll probably talk about psi another time. I think I did talk about it, but it was pretty hard to explain. Off of Cypher. I did not solve this problem. Let's see what Sam did. Sammy's taking cryptography classes, and his first project is to make an awful cipher. Being the good friend that you are, you have agreed to help write a decoder. Oh my god. Looks like what you have to do is just convert it with like a map or something. What's Sam do? Yeah, he literally just wrote it. Good. Great. Yeah, he just converted it. Looks like there's some value involved. I'm not going to talk about this. This seems boring. Oh my god. No, I'm not going to talk about boring. It's okay. Wordle is also kind of sucky too. I hate Wordle, or this version of Wordle at least. I'll explain why. Alright, so how Wordle goes is like this. Actually, there is some like complexity to it. So it's literally just like the game. It's literally the game, and if you get all wrong, if it's gray, it's X. If it's got it right, it's green. G stands for green, I think. It's G, and if it's yellow, it's Y. And then once you get it right, anything after that will become W. And then you also have to print this out, which is super annoying. They also have like all different types of messages. Okay. So I'm not going to go into it much, but what I did was I kept a map of all the characters and how many times they were in the array. So right here, if I did plugged in buggy, G, there would be a pair that said G, and then repeat it twice. That's the idea. I take an input of all the strings, and then if I've already won the game, I just print out W's. Otherwise, I have this like kind of string that has 5 letters in it. So first, I check whether if it's on point, if it's on the right area, and then I put a G in there. Then I take, so this temp array or temp map basically keeps track of the amount of letters, right? So Like, yeah. So if how do I? That's a good example. Like here, I think blocks is like good. 1, 1, 2, 3, 4, 5, 6. Okay, here. Oh wait, no. Actually, tarts is better. Here. So here, how it goes is like this: tarts and porch. Right. So she got none of them the first time. Or wait, yeah, she got the R right. Then there's Sandy. Yellow, green. And there's tight. T. Tight. Alright. So this keeps track of available letters. So like, once I've used up a letter, I'm going to subtract it from my map. Okay, so if I've used up a G, the 2 becomes a 1. Okay, so first I look for correct answers, like correct spot, correct letter. Next, if, then I go through the whole word again, and if it equals to, or if my print, or if it is the correct letter in the correct point, I continue. But if there are still some letters out there inside the word, right, this does not equal 0. So if it would equal 0 if all the G's went, like we found all G's. Okay. So all G's were in the correct positions. And yeah. So if there's still a G out there, but it's just in the wrong position, I'm going to put out yellow. Okay. And I change it to 1. Okay. So my Boolean will tell me it's wrong. And if it's just straight up not in the word, so if temp vi j is 0, it's not in the word, or all my G's have been used up, right? So if I had buggy and GGGG, what it would do is it would print out gray, gray, or XX, GGS. Okay. So these 2 G's are in the correct positions, but these X's, like these are just extra G's, and they're not yellow because all the G's have been taken up. They're gray because they shouldn't be there in the first place. Okay. Yeah. And then if it's wrong, so if I see yellow or a gray, this is just false. Change to 1, or if there's no wrong answers, I 1, and then I print out I store a variable called winning turn, and then I just type all this out. This is just BS. Before my test cases, I would print out this. That's just whatever game number it is. That was probably my least favorite. Split the vote was pretty interesting. Let's see what we got here. So split the vote, I did as well. So it kind of goes like this. So I use bit set. You really don't have to do that. Okay. I'm going to introduce a thing. It's pretty neato, but it's only in C++, so it doesn't matter. But it's pretty neat. The idea goes like this. So, and it's really small. It's really nice. Okay. But, how do I do this? Okay. So, basically, what's going on is you have a bunch of states. Okay, well, states in the US. Right, they're like blah 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 blah. Or 1, 2, 3, 4. First things first, you can omit 2 states. What happens is the 2 party omit 2 states. So let's do 2 and 3. Okay. Then what you do is you partition or you divide the rest of the states into two groups. So two groups could be like 1, 4, and then an empty group, or a 1 and then a 4, or that's it, like 4 and 1, but that's the same value. 4, 1, these are the same basically. So, the idea is you want to partition the groups such as the sum of all of them. The difference is minimal, so this difference is 5. The difference here is -3, but we're going to take the absolute value. This is 5 again, blah, 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 blah. So you want to make the difference as small as you can. So the correct answer for 1, 2, 3, 4, there's 2. You can either go through 4 and the difference and have a group like this. 2 minus 1 is 1. Or you can just go 1 and 2 and divide 3 and 4. And this seems tough, right? You don't know what to do. Yeah. Here is also pretty complicated. So how do I divide this? Well, first I have to omit 2 states, which is even more complicated. You can do like a bunch of other stuff. I'm going to omit these 2 actually. Maybe I'll get lucky and get it. No. What's the optimal solution? 5 and 9. How do you divide it then? 2, 8. Oh. Okay. Cool. But yeah, so the difference between 10 and 10 is 0. That's the idea. So how do you do it? Wow. This involves dynamic programming, so you may not be able to understand it, but it's okay. It's okay. So, yeah. So there is a problem called apple division on CSES, and I remember talking about it with y'all. It involves recursion. I remember if you pick 2 groups, you basically brute force it. So 2 can go to group 1 or go to group 2. Kind of deal. Same idea here, but a lot different. So how this works is kind of like this. So first things first, how do you omit? Right, the first barrier is omitting. Well, what I did was, since the n was so small, I just did a double for loop. Okay, so x and y. My x and y would be like 1 of them. So if x equals to y, meaning they're the same index, so if like x and y were both 1, that's not, we have to choose two distinct states. So we have to continue, that's not possible. But, yeah. So we basically choose a pair of x and y, and then we go on with that possibility. We brute force through every single pair of states, and then see what is the most optimal way of putting those states together. And the most optimal way goes like this. We basically go through everything together. Right? And what we do is we use dynamic programming to get all the possible sums. Okay? So what I mean by possible sums, it goes like this. Possible sums include 1, 2, 3, 4. So like 1, 2, 3, 4 by itself. Or you can have 1 plus 4, that could be 5. 2 plus 4, that's 6. 3 plus 4, that's 7. Can we make 8? 1 plus 3 plus 4 is 8. 2 plus 3 plus 4 is 9. And then all together is 10. So those are all the possible sums, which actually includes 1 to 10, which is a surprise. But the possible sums is basically if I picked out like a group of numbers, 1, 2, and 4, that makes a possible sum, and that would be 8, or 7. Right? And so we're going to get all the possible sums. Let me print this out here. This is my bit set called, it's called bit. Oh my god, it's huge. Okay. Change it to like 2. Oh wait, some. Let's do 11. I'll explain why it's so big. Okay, so this represents 0, right? There's always a way to make 0, right? You just have an empty set. 0 is just you pick nothing. Okay, that's why the 0 index is always 1. So if the number is 1, that means it's possible to make it. If the number is 0, it's not impossible to make it. So this first example should be 1 and 2, if you omitted 1 and 2. If you omitted 1 and 2, you can only make 3, 4, or 7. If you omitted 1 and 3, you can only make 2, 4, and 6. And this pattern goes on and on and on. Let's do one more. 1 and 4. You can only make... Wait. This is not 1 and 4. Is it 1 and 4? Oh, wait, yeah. You have 2 and 3 left. You can only make 2, 3, and 5. That's it. So this pattern goes on and on and on and on. And so if we can find this array, we can loop through all of these, right? We know that the value of group 2, or so the sum of all the states stuff is equal to, if we divide into 2 groups, group 1 plus group 2. Okay, got it. So we know group 1. Or actually, we can pick group 1 by selecting any one of these positions once. So for example, let's just pick 4, right? 4. That is a possible sum that we can add to the groups, right? And that can be our group 1. Okay, we know group 1, check mark. And in order to find group 2, we sum all the numbers, and then we subtract it by group 1. And that gives us group 2. Then what we can do is find the difference by saying the absolute value of group 2 minus group 1. Done. Okay? Then we compute the smallest difference. And the smallest difference of all those numbers will be our answer. Okay, so let's kind of go through it for an example. So the first bit set is if we excluded 1 and 2, right here. So I'm going to write it here. Okay. 0, 1, 2, 3, 4, 5, 6, 7. Okay, so it's possible to make 0 because we can just empty it out. It's possible to make 3 because we can just have a value of 3. It's possible to make 4. It's possible to make 7. Got it. So these are all the possible ways. Okay. So any one of these can be our group 1. Okay. So, in order to do so, basically, the sum of all the numbers left is 7. Okay. So if group 1 is equal to, let's say, 3, group 2 is equal to 7 minus 3, right? Because we're dividing into 2 groups. So it's 4. And the difference between 4 and 3 is 1. So that's the difference. Okay. One difference we can do is if we chose group 1 to be 0. Okay. And if group 1 is 0, group 2 is 7 minus 0, which is 7. So if group 1 is this, group 2 is actually going to be this. Make sense? And this is not really optimal because the difference between 7 minus 1 is 7, and we want the minimum possible. Right? Minimus. Minimal. Okay. So what we can do is we can loop through the whole bit set. Bit set is just a group of bits. Okay, like an array of bits. We're going to go through it, and if there's a 1, let's do the formula. Sum minus group 1, assuming this is group. Group 1 will be the index. It's group 2, and then we subtract group 2 minus group 1. Get our difference. That's going to be how it's going to roll. Right here. This is essentially group 2. I is the index, or group 1. Remember, the index represents whether it is possible to make that number based on the groups. Okay. Cool. So now, here's where the hard. So once you get this right, this is how we're going to do it. Now I'm going to leave this for last, but you may not understand how it works. It's perfectly fine. This next part, and this is where dynamic programming comes in. How do you get that bit set or that array? So this is actually really nice. I learned about it maybe like I remember I was doing the test doing this, but how it works kind of like this. So basically, I have, so the highest sum I can ever have is, well, m is the value that the highest value can be. Right, I think that's what it says. Yeah, I like those. So the highest sum is if all of them equal to 1,000, right? If we had an array of a bunch of thousands, that's our highest sum. And that equals 2. And the highest sum of the whole array would be 1,000, the maximum number times the maximum number of objects, which would be 20,000. That's that. Oh, wait, it's even bigger. 20,000. There we go. Plus 5. Just for good luck and make sure no array out of bounds. But yeah. So I set it all to 0. This is. And then I know we can make a subset of 0 because if we just don't add any numbers. Okay. So if the object is if it does not equal to, or if it's not omitted, remember x and y equals to omitted. If it's not omitted, what we'll do is something pretty cool. Okay. So I'm gonna. This is not how it works though. It's more like actually. What's that? 1, 2, 3, 4, 5. Let's do that. Okay, let's go back to the example of 7. So let's omit 1 and 2. So 0 automatically becomes 1. Okay, because it's always possible to make 0. Okay. Now what it does here, this line of code right here. So you see the shift right here. I'm going to shift all the ones by 3. Okay. And then I'm going to OR it. Okay. So this 1 stays here. But 1, 2, 3. Okay. I'm shifting by 3 because I'm going to go through all the elements of the array. Got it? So first I'll start with 3. 1. I'm shifting by 3. 1, 2, yeah. And then what I'm going to do is I'm going to change that 0 to a 1. I can make a subset sum, or a group of sum, a subset, or a group of numbers, group 1, Group 1 is able to be 3 if I just do this. If I make it into 1. Got it? Okay, now we're done with 3. Let's move to 4. I'm going to do is I'm going to shift all the 1s by 4. 1, 2, 3, 4. Change it to 1. Now, this is not going to only happen there. It's also... Actually, I'm just going to undo. I'm also going to shift this one. Remember, this is the new one, so we're not going to shift it at all. But I'm also going to shift that one by 4. 1, 2, 3, 4. So every time you see a 1 that hasn't been placed on that turn, I'm going to shift it by that number. Okay. And you'll notice we get the perfect array. And if it's 1, we can reach it. If it's 0, we can't. Voila. So yeah, that's why I like bit sets. This shifting, this binary shift, is not just in your MCQ. It's actually pretty applicable in dynamic programming. And there's actually a lot of connections between it. And that's why it's like one of the reasons why I like doing this. Yeah. I also compute the sum while I'm at it. If it's not equal to x over y, I'm just going to do the sum. That'll be 7 in this case. But yeah, that's how you do your bit set. That was a long one. Far from home I did not do, but it looks like it's a graph problem. So let's see. A favorite pastime for the young octopi is reef riding. The reef consists of n locations, each with their own current, and carry babies to a new location. These currents will potentially be dangerous though, so parents form untimely demise, blah blah. Decided to location L is deemed safe if and only if any location reachable via current from L can be reached by riding L's K current starting at L. If and only if any location reachable via current. I'm confused. So I'm going to pull up my graph editor. It's a website that I use pretty frequently in graph problems. But it's also lagging, which I don't like. Come on, it usually doesn't lag. I think it's just because I'm screen sharing. Okay. First line of input contains 2 space integers and a k. K is what? Currents. Or currents. One, 2, 3, 4, 5, 6. Okay. Yeah, this is what it looks like. Oh, okay, I see what it is. this looks like what it's going to be. So what it means is, if I started at location I, so I would be 1 in this case, or 2, 3, 4, whatever index, I can go to location 3. So look, island or location 2 can go to location 3. And if we imagine each location as a node on a graph, it would be actually really nice, like this. It's a little messy though, and there's just too many nodes, but it's fine. Okay. Locations 6 and 11 take 7 steps to reach 5. All of the locations are safe. First things first, there will be cycles. Like 7, 6, and 8 will go in a cycle. Because we know this because each node has a place to go. It's greater than the tree, but it's fine. You don't need to know that. Okay. Remember locations deemed safe. One, 2, 3, 4, 5. One, 2, 3, 4. Wait, what? 1, 2, 3, 4. Did I do it wrong? 2, 3, 4, 5, 1, 7, 8, 1, 10, 2, 12, 8. I did it right. One, 2, 3, 4. Or maybe it's corrected. Oh my god. 5. 1, 2. 1, 2, 3. The description of each location is current. Can you determine how many locations are safe? Any location reachable will be a current from L can be reached by writing the most K currents starting from L. What? I don't get this from. What the heck? How did Sam solve this? Can you determine how many locations are safe? So it's safe if only any location reachable via current from L can be reached by writing at most K currents starting from L. Three, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4. It takes 7 steps? How do you take 7 steps? One, 2, 3, 4, 5, 6, 7, 8, 9. Wait, 1, 2, 3, 4, 5. What? Let's see what Sam did. I'm gonna cheat. This is usually when I would ask Sam for help or something for explanation, but let's see what he did. So this is what's called a functional graph. Don't always one way. So it is directed. Okay. Oh, so if the cycle is so if the cycle is greater than 5, is that what I'm getting? 1, 2, 3, 4, 5. Or greater than k. So 11 is assumed to be not good. 1, 2, 3, 4, 5, 6, 7, 8. I mean, that's what Sam did. Seven steps to reach location 5. 1. Oh wait, 12 has 2. Why? Stop. 12 has 2. Why? I was a misprint. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Why does 12 have 2? 12 to 8, 12 to 8. 12 to 6? Oh, no, it shouldn't have 12 to 6. Bruh, that screwed everything up. Okay, let's go do this again. 6 and 7 take 7 steps to reach 5. 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Oh, okay, good. 7. 1, 2, 3, 4, 5, 6, 7. Okay. That makes so much more sense. I see what Sam did. Everything makes sense. Yippee. Okay. So, basically, what you do is you go through all these nodes and make sure that you can reach back home. Or what? What did Sam do? It was back home, right? Oh, okay. I haven't visited it yet. So basically, I'm going to go through this whole situation, and then if I go back to a position that's already been like seen, then I edit. I understand the problem, but the explanation is going to be weird. Okay. Essentially, we're going through every node, and then we're going to go. It says every location can go to one other location through a current. That means we're gonna compute the like some places can't go to some places, right? 9 is not reachable, right? I can't go anywhere to 9 right here because there's no destination to 9. You'll notice that the node like connections. 1 goes to 2, 2 goes to 3, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1, blah, blah, blah. It looks like that. I know that because it says ith of which will go to the ith location. Yeah. Basically, you go and follow these arrows, and if it goes in such a way that is greater than k, that node is not safe. Okay. And it keeps on going until it finds a place that hasn't been or has been before. So for example, let's just take out this. Okay. So I start at 1, I'm going to go to 2. There's only one way. 2 goes to 3, 3 goes to 4, 4 goes to 5, and 5 goes back to 1. And since we've already been at 1 before, the loop ends. That's the idea. Sam did it in his own way, which is pretty nice. It's a pretty good solution. This basically means it goes to wherever it goes. Like, let's say the index is 5. Our index would be 1. So the index changes from 5 to 1. So that's the arrow movement. 5 to 1. If I visited, or if I've like been there before, for example, like I was at 1 before, I'm going to break, and if the amount of steps it takes is greater than k, that is not a good node, or not a safe node. That's far from home. I didn't do far from home, but Sam probably had a ball. Khadgar I did do though. It's a little bit easier. So how Khadgar works is kind of like this. This guy, he has 2 byte strings, bit strings, and you want to make it so that you can convert one bit string to another. Okay. So first things first, if it's possible, you can do the following moves: this to that, that to this, this to that, and this to that. So any substring, he can convert to the other substring. If it's possible, he can do this action, these actions infinite amount of times. And if it's possible, print yes. If it's not possible, print no. So, is there any cool, like funny solutions like that? Or no? Okay, whatever. There's like, you may think of trying to like brute force this, but there really is a pretty simple solution. And you'll notice that all of his actions are basically just reversing it. Right. And every time you reverse something, if we just like look into this. Keep track of the indices. The parity of the numbers don't change. This one stays even. This one stays odd. And basically, every time you reverse it, you can switch all these numbers around all you want. It's just that any one will always stay odd, any even will always stay even, or any odd will always stay odd, any even will always stay even. So what I do is I count the number of evens in first string, count the number of odds in second string, evens in second, or blah blah blah. And if they equal to each other, like the odds equal to each other and the evens equal to each other, it's possible. Otherwise, it's not. And I take it from perspective of the ones. If I just change this to 0, it'll be the same thing, because there's only ones and zeros. That's it. And you'll see that every time you switch around a bunch and all that stuff like that, you can make any string through these actions, these reversals, as long as the parity stays the same. That's it. Yeah. That is the UTD contest. Some of the explanations were but I hope you had fun, and I hope you liked watching me in classes. This is my blue light glasses, so they make my eyes feel better. See you guys.